Thanks. And now we move on to the next speaker of this morning session, who is Alison Tezzin. Please, Alison, if you can start sharing your screen.
Hi. Okay, can you hear me?
Yes, perfectly. And also, perhaps it's better if you put a full screen mode.
Okay.
Okay, so the next speaker is Alison Tezzin from the University of Sao Paulo, Brazil. And he's talking about, are we witnessing non-local phenomena when non-contextuality inequalities are violated? Please, Alison, go on.
Okay, so I'd like to thank the organizers for having accepted my talk, and congratulations for this very nice conference. And it's a pleasure to be here. And so, as you see, this talk is about a question. And the question is if we are witnessing non-classical phenomena when non-contextuality inequalities are violated. And I would like to begin this presentation by justifying this question. And in order to do that, I will show a couple of examples of very recent papers where this claim is made. So the claim that contextuality, which means, by which I mean the violation of a non-contextuality inequality, is some kind of signature of non-classicality. So these are the examples. So contextuality is a non-classical behavior that can be exhibited by quantum systems. It's a non-classical feature challenging everyday intuition. It's a non-classical property exhibited by quantum statistics. It's a key signature of non-classicality. And finally, it's the archetypal non-classical feature of quantum phenomenology. So we know that this is a quite common view. And in order to contrast contextuality and classicality, let me explain what I mean by classicality. And I will do that basically by quoting this paper. And okay, and the main point is that, as I see it, a criterion for classicality must have a phenomenological meaning. So as they say in this paper, a criterion of classicality must allow us to say that in some sense, nature fails to respect classical physics. So non-classical phenomena must defy classical understanding. And this is basically what I expect from a criterion of classicality. So we can now rephrase our initial question just to be more explicit. And we are asking if nature fails to respect classical physics when non-contextuality inequalities are violated. Okay, so now let's discuss non-contextuality inequalities. And this definition of contextuality, that is the violation of non-contextuality inequalities, it's a very operational definition in the sense that it's a definition we apply for experimental data. So contextuality.
Wait, there's something. I will try to mute Federico. Everyone, please mute their phones. Sorry, Alison, please go on.
Okay. Okay, so as I said, this is an operational definition in the sense that it's a label we apply for experimental data. And this idea of contextuality as something that we can apply for data with no reference to the underlying structure of the mechanism we are working with, it's a definition that arises in the context of this model-independent approach to physics. So I will discuss this model-independent approach very briefly because I think some of you may not be familiar with it. And the core idea behind a model-independent approach to physics is this idea of a black box. And a black box is a measurement setup. And we call it a black box because we assume that we can ignore the underlying structure of this setup and we can look only to the data. So as Popescu says, according to this view, the entire physics should be encapsulated in the data. And we can discuss, for example, locality from this perspective. So we can discuss locality beyond quantum mechanics, so with no reference to quantum systems. So all we need are devices and measurements that are outputs. And we can also discuss contextuality in this perspective. And this is exactly the definition of contextuality that is based on non-contextuality inequalities. So contextuality is the violation of non-contextuality inequalities, just as non-locality is the violation of Bell inequalities, or we can equivalently say that contextuality corresponds to the obstructions to the existence of global sections. So this is equivalent to say that contextuality is the violation of non-contextuality inequalities. So, okay, and just to make it clear that this idea of black box appears in contextuality analysis, I will show 2 examples. So here they say that we have a black box and that the agent consumes the box by simultaneously performing a subset of measurements, and a subset of measurements that we can simultaneously perform is what we call a context. And here they say the same. So we have a black box that is a device containing buttons and lights, and buttons represent measurements and lights represent outcomes or outputs. And we have contexts that are collections of buttons that we can press jointly. And okay, so these are some pictures representing this idea of black box in contextuality analysis. So here we see that we have a black box with inputs that are buttons or measurements and outputs that are represented as lights. So, okay, so this is basically this model independent view. And now we will show a particular example of black box. And we will discuss this example using the compatibility hypergraph approach to contextuality. That is one of many model independent approach to contextuality analysis. And we have to introduce a measurement scenario in order to define a black box. And the measurement scenario we consider is a very standard example of a measurement scenario in contextuality analysis. That is the 5 cycle. So in this scenario, we have only 5 measurements. And all measurements of this scenario are binary. So they have only 2 possible outcomes. So 1 and 0. And this is the symbol we call 1. And this is the symbol we call 0. Okay. And we also have to define a context. So recall that a context represents a collection of measurements that can be measured simultaneously. And these are the contexts we consider in the 5 cycle. So a context in this scenario is a pair of consecutive measurements. So for example, A1, A2 is a context, A3, A4 is a context, A4, A0 is another context, and so on. So we have 5 contexts. And as I said, this is a very standard example of measurement scenario for contextuality analysis. So these measurements are like the buttons of our black box. And now we have to introduce a behavior for the scenario that is the data our black box generates. And the behavior we consider is a very famous example of contextual behavior in the 5 cycle. And the behavior, and it's this behavior. So by definition in contextuality analysis, the behavior of a scenario is context dependent. So we associate a probability distribution for each context. And this is the distribution we associate for a context in the 5 cycle. So if we measure together AI and AI plus 1, we will never obtain the same outcome. And the probability of obtaining 0, 1, or 1, 0 is the same. And this is the data our black box generates. So this is the behavior of our box, And okay, and what we can say about this behavior? So first of all, it's non-disturbing, which means that according to this behavior, it means that a measurement has the same distribution across all contexts. And moreover, according to this behavior, a measurement behaves like a coin toss. And this is one of the reasons why we are calling this behavior a generalized coin toss. This behavior is an example of stronger than quantum correlation, which means that quantum theory cannot predict this behavior. And finally, this behavior is contextual. So it violates a non-contextuality inequality, or equivalently, we cannot define a global section for this behavior. So it means that we cannot define a probability distribution, including all measurements of this scenario, that is capable of predicting this behavior. So, and this is an example of maximally contextual behavior in the 5 cycle, and this is why this example is very famous. Okay, in the compatibility hypergraph approach, contextuality and non-classicality are equivalent definitions. So according to this approach, if our black box generates this data, then we have to say that our black box generates non-classical correlations. Okay, so thus far we have discussed contextuality from this model independent view, and we have showed a very famous example of contextual behavior in the 5 cycle. So this is the data our box generates, and this is the data we are going to analyze. Okay, but now let's look inside the box, and to begin with, I would like to compare Bell inequalities with contextuality inequalities, because as I said, contextuality, according to this definition, is the violation of non-contextuality inequalities, just as non-locality is the violation of Bell inequalities from this model independent perspective. So let's compare these two definitions. So suppose we have a Bell scenario. So it's a scenario containing 2 space-like separated parts. So each part has a black box, and each part is performing measurements, and they are generating data together, and we analyze this data. And if this data violates a Bell inequality, we can say that we are witnessing a non-local phenomenon, which means that and locality or non-locality is a physical concept in the sense that we can define it in terms of physical principles. For example, we can define locality using special relativity. And in this case, the data we have is intrinsically associated with a physical phenomenon, and we can really ignore the underlying structure of these boxes. So these measurements, they can be, for example, questions, yes, no questions we ask for these agents, and these outputs can be answers they give. And even in this case, if these Bell inequalities are violated, we can say that we are witnessing non-local phenomenon. So there is this physical phenomenon associated to the data we have. But in contextuality analysis, we have no physical phenomenon associated to it, because contextuality, according to this model independence definition, is not a physical phenomenon, because we cannot define it in terms of physical principles. So it would not be a surprise if inside a box generating non-classical correlations or contextual correlations, we had a simple classical structure. And I will try to show now that this is the case for the behavior we called a generalized coin toss. Okay, and before we go through the example, I would like to say 3 things about it. So first of all, recall that we are assuming here that everything is encapsulated in the data, so we can, in some sense, ignore the underlying structure of this black box. So a black box is a very permissive concept, so it may contain an entire laboratory containing particles and measuring devices. And also, the mechanism we propose is basically a toy mechanism for coin tossing. And coin tossing is, according to many operational approach to physics, it's a valid example of measurement procedure. So for example, people who work with specking contextuality and generalized probability theories, they are all the time using coin tossing as an example of measurement procedure that is valid. So, and that's why we say that this mechanism works along the lines set out in many operational approaches. So according to this approach, if we had inside a black box a coin flip, a coin tossing, it would be a valid measurement procedure. And more importantly, this mechanism is something like a thought experiment. So we are trying to show that unlike non-local data, non-contextual data can be generated by a simple classical mechanism. So this mechanism should be understood as a thought experiment. So it's not a mechanism that is interesting by itself. So, okay, now let's go through the mechanism. And as I said, it's basically a toy mechanism for coin tossing. And how can we describe a coin toss using a toy mechanism? So we need an object. So in the real world, we use a coin that is an object that for all practical purposes has two sides. So here in this toy mechanism, we consider, for the sake of simplicity, a 2D object, and each has two sides. So one side is dark gray, the other side is light gray. And we need to flip this object. So we fix an axis passing through the center of this object, and we flip this object. And at the end of the movement, we look to the side that is showing when the coin lands. So this is the real case. So in this toy mechanism, we fix this side of the object. So, and we imagine that this is a sensor, and the sensor can detect color that in this case is gray. And it can distinguish dark from light color. So we have these two outputs. So these outputs are like heads or tails. So they are dark gray or light gray. And the behavior we obtain if we perform these measurements. So if we flip this coin, is the behavior of a fair coin flip, because this mechanism is constructed for this purpose. So, okay, so this is a toy mechanism for coin tossing. And the point is that we can propose a straightforward generalization of this mechanism that is capable of generating the behavior we called a generalized coin toss that, as I said, is a very famous example of contextual correlation in contextuality analysis. So in a coin toss, we have one binary measurement. So we need an object having one pair of oppositive sides. But in the generalized coin toss, we have 5 pairs of oppositives. So we have 5 binary measurements. So we need an object having 5 pairs of oppositive sides. So it could be something like a 10-sided dice or something like this. But we are proposing just a toy mechanism. So we consider a 2D object, and this is a regular decagon. And for each pair of oppositive sides, we associate a measurement. And for its measurement, we associate a color. And okay, and the measurement procedure inside of this box is a coin flipping, but the flipping is determined in this case by the context. So the context in this toy mechanism is an axis passing through the center of the object, and together with a sensor, and the sensor can detect color and it can distinguish dark from light color. So for example, if we want to measure a 2 and a 3 together, if we press these buttons in our box, this mechanism will just flip this coin, but with respect to the axis determined by this context. So this is the axis, this vertical line. And if we do that, we can obtain 2 possible outcomes. So we can detect dark yellow and light green, or we can detect light yellow and dark green. So we can never detect, for example, dark yellow and dark green because they are in opposite sides of this object. So this is a mere geometrical restriction of the object. And this is why we have this, we have the correlation that is predicted by the generalized coin toss in this context. And this is the mechanism we have. So each context is an axis together with a sensor. And whatever is the context we consider, we have only these 2 possible outcomes, and the behavior is the behavior we called a generalized coin toss. Okay, and we also must be able to perform single measurements. And in order to do that, we have to fix a context. So this is the general case in contextuality analysis. So for example, if we want to measure these measurements A0 that is red, we have two options. So we have 2 contexts containing A0, and we have to choose one of them. So we can choose, for example, this context, and we just flip this object. And So we have two possible outcomes, so dark red or light red, and the behavior is the behavior of a fair coin flip. So to sum up, this mechanism, this toy mechanism, or this thought experiment, generates the behavior we called a generalized coin toss. And okay, and what we can say based on this example, based on this thought experiment. So first of all, let's discuss contextuality beyond quantum theory. Okay, so the first point is that without a clear specification of what measurement means, contextuality has no phenomenological significance, which means that the meaning of contextuality, or the phenomenological meaning, depends on what we mean by a measurement. So in contextuality analysis, the underlying structure matters. So we cannot say that, I think that based on this thought experiment, I think this thought experiment suggests that we cannot ignore the underlying structure in order when we are analyzing data from this perspective of contextuality. Which means that in contextuality analysis, the entire physics does not seem to be encapsulated in the data. So what we mean by measurement is important. And finally, contextuality, at least beyond quantum theory, does not require a non-classical phenomena. Okay, and can we say something about contextuality in quantum theory based on this thought experiment? And I think we can. So note that in our thought experiment, we are working with a classical object. So it's basically a coin. So it's a classical object in the sense that it's a rigid body. So it's just a toy mechanism. So we say it's a 2D object, but we can imagine it as a real body, just as we imagine a coin as a rigid body. And okay, so we have this classical object, and measurements, our measurement procedures, are not revealing properties possessed by the system. And also we have context. So not all measurements can be simultaneously performed. So we have this restriction that is a instrumental restriction. So this is part of our mechanism. So it means that in our thought experiment, we are working with measurements that I like to call epistemic, that are measurements that are not revealing properties possessed by a system. And we know that this view on measurement is a very common view on quantum measurements, because we have Cauchy-Specker theorem, and Cauchy-Specker theorem says that self-adjoint operators cannot be thought of as representing properties simultaneously possessed by a system. So Cauchy-Specker theorem suggests some kind of epistemic view on measurements. So we have to accept that measurements are not revealing properties possessed by a system, or at least that they are not revealing properties that are simultaneously possessed by the system. But the point is that if the measurements we have are epistemic, so if the measurements we have are not revealing properties of a system, then we have contextuality in the data. So the data our system generates will violate non-contextuality inequalities. And it's not because the system is non-classical or it's classical, it's because measurements are epistemic. And the reasons that epistemic measurements cannot be defined as random variables sharing the same sample space. So we cannot define the measurements we call the measurements that are like coin flippings in our thought experiment. We cannot represent those measurements as random variables in the same sample space. And that's why we have contextuality in quantum systems, I think. And we must recall that KS theorem, Cauchy-Specker theorem, is about realism. It's not about classicality. So to sum up, in quantum mechanics, we have, so if it, in general, actually, if we have epistemic measurements, so if we have measurements that are not revealing properties possessed by a system, and if we have context, so if we have these restrictions on what we can measure jointly, then we have contextual data. So we have no ground for expecting non-contextuality in the data, because our measurements are not random variables in the same sample space. So I think that this thought experiment suggests that those who accepted the abstentive view on measurements, that is the view suggested, for example, by the orthodox interpretation. This is the view held by Bohr, and this is a very widespread view on measurements in quantum mechanics. So those who accepted this view, I think that should not take for granted that nature fails to respect classical physics when quantum systems violate non-contextuality inequality. So it seems that these violations are actually a consequence of the type of measurements we are considering. And if we accept that the measurements we have in quantum systems are epistemic measurements, then we should not say that nature fails to respect classical physics when these violations occur. And that's it. That's what I had to say today. And thank you.
Thanks, Alison. Thanks for this talk. So we have some time for one short question, because now we are on 9:56. So if someone has a question, please go on. So I have a question, or perhaps an observation, which is you can see the violation of Bell inequalities as a particular case of a non-contextuality inequality, right? Because and when you speak about model independence, it is not so independent of physical laws, because in model independence you have space-time structure. So this is not stressed usually in the literature about it, but otherwise, if you don't consider the space-time structure, you cannot speak about a model independence analysis of an Alice and Bob scenario. You cannot even speak about space-like separation between measurements, you know? And so what I think regarding your talk is that perhaps this space-time causal structure should be taken into account into your analysis. I agree in that if you don't take space-like separation, you can reproduce everything with a classical mechanism. I think that is accepted, right? I mean, because you have examples of contextuality in, for example, in mathematical psychology and so on. That I agree. But even so, I think that you can include the violation of Bell inequalities as a particular example of a violation of a non-contextuality inequality. So what do you think about that? That cannot be reproduced by any classical mechanism. What do you think about that?
Yeah, no, yes, I agree. So that's why I compare Bell inequalities with non-contextuality inequalities. So I know that Bell inequalities are particular cases of non-contextuality inequalities, but I just say that this idea of black box works very well if we have space-like separated parts. So I agree with it. But if we have a black box that is localized, so as the kind of box people use when they are discussing, for example, resource theory for contextuality. So we have this box with many inputs. So in this case, if we have contextual data, we not necessarily have non-classical phenomena or something like this. So, but I agree with it. So if the boxes are space-like separated, then we need non-locality.
I see your point. Okay, I will check on the details because you have a paper on this I've seen on the web. So I will check, but next week. So, okay. But now we are on time. So we thank again Alison for this nice talk. And
thank you.
Thanks, Alison. So now we call Diego to share your screen. Okay. So please, Alison. Okay, great. So thanks, Alison. So now we are on time for Diego's talk. Great, great. So now we are glad to have Diego Busandri from the Institute of Physics La Plata and the National University of La Plata. And he will speak about revisiting maximal fidelity of teleportation. Please, Diego, go on.
Thank you, Fede, for the presentation. So let's talk.
Diego, wait. Yeah. Your sound is low. You could speak like this, and it's good, but if you could...
Now?
Yeah. Now it's much better. Thanks, thanks. Please, come on.
Thank you, Fede. Oh. Sorry.
No problem, no problem.
Now, okay, let's talk about fidelity of teleportation. This is a work we made with Mariela Portesi and Anna Mattei. And so what did we do? We obtained the maximal average fidelity of teleportation, or the score of a given protocol, for two situations. The standard quantum teleportation protocol, characterized by a particular measurement. So, 1 second. Now, we calculate the maximal average fidelity of teleportation for
the sound is again low. I don't know if everyone is.
What happened now?
Yeah, now it's better. Yes.
Sorry.
No problem. No problem.
Then we obtain the average fidelity in two situations: the standard quantum teleportation protocol, characterized by a particular measurement, in which there is a projection onto the bell basis, and another protocol whose characteristics measurement is something in the middle between the computational basis and the bell basis. But our differential feature is that we calculate this for isotropic distribution of input states, not only the hard measure. I mean, not only pure estates. So we are going to talk about useful protocols, namely a protocol is useful when its average fidelity is greater than the classical one. Our key point, or our main result, is that when you take an average over a more general distribution than the half measure, the quantum teleportation protocol can be useful when your resource has no quantum correlation. So even for a classical quantum estate. Well, what is the meaning of fidelity of teleportation? Let us suppose that we have a protocol P producing output state given by rho out with probability pi for an input state, or a qubit state given by rho a. And rho a is characterized by its Bloch vector T, okay? And so if you want to know how well the quantum teleportation was performed, you can quantify the similarity between rho a and the final outputs, calculating equation 1. But this measure